Let's revisit how to do the calculations portion of lesson 115. Just to remind you, the whole point of this lab was to figure out whether ethanol or isopropanol released more energy per gram to water. So we set up this experiment by burning the two different fuels underneath a can of water. And we made the assumption that the potential energy from the fuel was converted into thermal energy, which transferred to the water. We would blow up our thermometer if we just put the end of it into the alcohol flame. But water has a really high specific heat. It takes a lot of energy to change its temperature. So we can safely put a thermometer into water and not have it be damaged because it won't get as hot. How do we do that? Well, scientists know exactly how much energy it takes to heat up 1 gram of water by 1 degree Celsius. So if we know how much water we have in the can in grams, and we know how much it changed in temperature, we can calculate the exact amount of energy that it took. So here's a little example. Let's say you've got your 1 gram of water and the temperature goes up by 1 degree Celsius. Again, we know that that takes 4.2 joules of energy. So this little sample problem that they're giving you, they're telling you, okay, you've got 50 grams of water and you want to increase the temperature by 10 degrees Celsius. How much energy is that going to take? Well, we can do a simple multiplication. Since we know 4.2 joules is enough energy to heat up 1 gram by 1 degree Celsius, we can multiply it by 50 grams and 10 degrees Celsius, and we get 2,100. Now let's look at our units. Grams cancels out, degrees Celsius cancels out, and we're left with joules. Mystery solved. This would take 2,100 joules. The formula that we're really writing out is the amount of energy required to heat up that water is equal to the specific heat, again that value that scientists determined, that 4.2 number, never changes. We're multiplying it by the mass of the water and the change in temperature. Now, to make it easier, scientists use variables. So we can skip number 6, and in number 7, we'll write out the actual equation. E, you would think would be the variable, but it's Q for energy, quantity of heat. Specific heat you might think is an S, but it's actually C, times, finally one that makes sense, mass is an M, and the change in temperature is delta T, triangle T. Sometimes you'll see this written as MCAT, meaning MC delta T, because it kind of looks like MCAT. And so just to give you a heads up, you might see that equation written that way. So, pro tip, you can actually use the snipping tool. I'm going to hit new and demonstrate this again, and grab your data. It automatically copies it for you so you can minimize, and you can paste it right next to where you want to refer to it so you don't have to keep scrolling up and looking for that. So let's do some calculations. Trial 1, ethanol. How much energy was given to the water? Well, we're going to use our equation. Q equals specific heat times the mass of the water times the change in temperature. Now, this is going to be pretty easy because the mass of the water over here was always 100. So that number is not going to change. And we're going to be using the change in temperature values in our calculations here. So I'm going to highlight those yellow. Let's plug some numbers in. So it's always going to be 4.2 for the specific heat times 100 for the mass of the water. And for my trial 1 for ethanol, I can see it was 34 degrees Celsius. I get 14,280 joules. I'm going to do the same thing for trial 2. 4.2 times 100 times the change in temperature was only 33 for that one. That comes out to be 13,860 joules. Repeat for isopropanol. Same thing. 4.2 times 100 times by the 43.5, and I get 18,270 joules. And for trial number 2, for isopropanol, 4.2 times 100 times 44, that is equal to 18,480. Now you might think you're done. You've got your answer. Oh, look at isopropanol numbers were bigger. So that must mean that isopropanol releases more energy. Well, we're not done, because what if those experiments ran longer and it just gave more energy to the water because you were burning more fuel, right? More fuel, if you burn it for like 10 minutes, let's say, the energy of the water is going to go way up. So you have to take that into consideration. Also, these are big numbers. So the next step is actually going to be to divide these by 1,000 to get them into kilojoules. So for trial 1, I'm going to just take that exact value, 14,280, and divide by 1,000. That's 14.28 kilojoules. And I'm going to repeat that for all of these trials. This one comes out to be 13.86 kilojoules. This one is 18.27 kilojoules. And my last one here is 18.48 kilojoules. I like step 3 because it says calculate the mass of the fuel used for each trial, and we literally already did that. So I'm just going to recopy those numbers down over here. We've got 1.3 grams, 1.29 grams, 1.55 grams were used up, and 1.45 grams. Now we're actually taking into consideration how much fuel burned in order to release that much energy to the water. So this will make it a fair competition. So for ethanol, we'll take that 14.28 kilojoules and divide it by how many grams were used, 1.3 grams. And punch that into my calculator. That comes out to be 10.98 kilojoules per gram. Do the same thing for my next one, 13.86 kilojoules, and I'm dividing by the 1.29 grams, and that comes out to be 10.77 kilojoules per gram. Next one, I've got 18.27 kilojoules divided by 1.55 grams, and that brings it down a little bit, 11.79 kilojoules per gram. And my last one, 18.48 kilojoules, while 1.45 grams burned off. That gives me a value of 12.74 kilojoules per gram. Now, we did 2 trials of each to try to get good data, and so now we're going to find the average. So to find the average for ethanol, I need to take my 2 values and add them together and then divide by 2. So this one I get comes out to be 10.88 kilojoules per gram. And the average for isopropanol, 11.79 plus 12.74 divided by 2. In the end, isopropanol, according to my data, gave off more energy per gram. So for my conclusion, I'm going to answer the question, which released more energy per gram? So I would say for my first sentence, isopropanol released more energy per gram. And my data to support it would say my results showed that isopropanol released 12.27 kilojoules per gram, while ethanol only released 10.88 kilojoules per gram. It's important to cite your exact numbers. And for my reasoning, I can see from the structures that isopropanol actually has 3 carbons, while ethanol only has 2. We don't know all the exact reasons yet, but I could make a little bit of sense of it by saying that isopropanol releases more energy per gram because it has a larger molecular structure. And then confidence in my results, I might say I feel confident in my results because our group did not have many random errors that occurred. However, we did forget to change the water between trials. That could be an example of a random error. A systematic error is something that we can't really avoid no matter how hard we try. So, for example, a lot of the energy from the alcohol did not just go directly to the water. Some of it was transferred to the air and to the actual metal in the can. And hopefully this brings it all back to that whoosh bottle when we were talking about which whoosh bottle was more powerful, the ethanol or the isopropanol. This experiment might actually help us figure out which fuel does release more energy per gram. And scientists ask questions, so you should have more questions, and it can even be things like, how do they make ethanol? Something like that. Number 3, I would not agree with this student because they said that the one with ethanol must contain more energy. And according to my results, that was not the case. And last but not least, the check-in. For your little picture, you might have your alcohol burner with the wick and the fire and the water. And we can say that potential energy in the fuel was transformed into thermal energy. That's the transformation. Some of it was also transformed into light. The thermal energy from the fuel was transferred to thermal energy in the water. That's what we were measuring, and that's where we were hoping most of it went. However, some thermal energy from the fuel also went to heat up the air in the room. And some thermal energy from the fuel went to heat up the metal in the can. And the homework questions are a separate YouTube link, so you can check that out if you need help with those.